Now, you did have one word problem in the homework that I had not done one just like it, but I decided to leave it in the homework for two reasons. The main one being you have a view example button, so you could see it if you needed it to. And another thing, you had already worked with the equation. In 6.3, when we were covering exponential equations, you had some word problems, and I said, yes, the problems have words in them, but really they're just giving you a number. You plug the number, a number into a formula and then punch it on the calculator. Well, in 6.4, you had to do a little bit to get the variable by itself before you could punch it on the calculator. For example, we need to do a couple more problems from page 448, and then we can start 6.5. Number 117 gives you a formula for calculating the pH of a chemical solution. No. Yeah, this is pH, the acidity or alkalinity of a substance. And all I can remember from my high school chemistry days is that 7 is the magic number. A substance with a pH above 7, those of you who are in by, that's acidic, and below 7 is basic. Okay, just asking for confirmation there, because I honestly don't remember. I just remember 7's the magic number. In the book, they've written log base 10. I really can't figure out why, because log without a written base is understood to be base 10. So maybe they put that in there for folks who skipped the previous part of the chapter. I don't know, but you don't have to write that 10, and it still means log base 10. H positive is the hydrogen ion concentration, which determines the acidity or alkalinity of a substance. So in 6.3, I could have given you the hydrogen ion concentration of a substance, and then it's just a punch on the calculator problem. I'm not even going to write it down, but the A part says, what is the pH of a solution for which the hydrogen ion concentration is 0.1? That just means put 0.1 in place of this and punch on the calculator negative log of 0.1, and you have the answer. Now, in the E part, we're supposed to find the hydrogen ion concentration of an orange, given that the pH of an orange is 3.5. That means I need to put the 3.5 in place of pH and solve for the hydrogen ion concentration. So 3.5 equals negative log of the hydrogen ion concentration. How am I supposed to get that H plus by itself? That's the scariest thing you could possibly say to a math teacher, and I'll tell you why. That makes me think that you think log of something means log times something. And it doesn't. If you say log of 100, that doesn't mean log times 100. That means tell me the exponent of 10 that would give me 100. So since this is not held together by multiplication, you can't solve for 100, for example, by dividing by LOG. Dividing by LOG doesn't make sense without an argument. So I paid you to say that just so I could explain, right? Okay, all right. What else? What if, Kevin, do you have an idea? What if I tell What if I tell you the first step and you help me think of the second step? First, you need to get the logarithmic expression by itself. That means you need to get rid of that negative. If I said, for example, 3.5 equals negative p, how would you get p by itself? Divide by negative 1. That's what you need to do here. Divide both sides by negative 1, and you have negative 3.5 equals log of the hydrogen ion concentration. Now, can anybody think of how to solve for that H plus? That's it. Ooh. Exponential. Yes, change it into exponential form. Now, the book has that 10 written for you, but even without it, you should know that this log with no written base means base 10. So what would you have when you change that to exponential form? All right. All right. The base is 10, the exponent's negative 3.5, and 10 to the negative 3.5 will give you the hydrogen ion concentration. So hydrogen ion concentration is 10 to the negative 3.5. And then it's just a calculator problem. Somebody punch 10 to the negative 3.5 for me and give me the hydrogen ion concentration of an orange. All right, it was 316. I don't think we were told specifically what to round to, so I'm just going to give 3 significant digits. 316. All right. Let me show you something about number 100. Yes, sir. Ooh, I didn't ask for a second. 10 to the negative 3.5. What are you getting, Courtney? We didn't need E. Oh, your answer, I know what you're saying. Your answer is coming up on your calculator, 3.16 E negative 4. Okay, I'm glad you told me that. What does that E mean when it pops up in an answer on your calculator? That's your calculator's way of writing scientific notation. That means 3.16 times 10 to the negative 4. In scientific notation, or in standard notation, move that decimal 4 places to the left, and that's the same thing. So, Courtney, is that what you were getting this, but now you understand it's the same as that? Whenever the E pops up. That E pops up a lot in statistics, and I've been telling them all semester, don't panic, that's just scientific notation. I still get emails every time an E pops up. I have an E in my answer. Scientific notation. All right, let me show you something about 120. We have a formula that we also had in 6.3. Healing time of a wound. N stands for a number of days. A stands for the area of the wound, and I think it's measured in what? In millimeters, square millimeters. So in 6.3, I could say find the area of this wound in 3 days. You just put 3 in the place of N and then punch it on the calculator. Now that we know logarithms, though, instead of giving you the N, I can give you the A and ask you to find N. The A part of this problem says determine, let's see, if healing is taking place, after how many days will the wound be half of its original size? By the way, in the book, the original formula has A sub 0 right there for original size, but then in the next sentence they told us the original size is 100. So this is a wound that started out 100 square millimeters, and we're looking for when it will be half of its original size. The word when tells us that we're trying to find this number of days. We're solving for n. If we're going to solve for n, I have to have something to put in place of the a, and I'm telling you it's not 1/2. What is it if 1/2 is the wrong thing to put in place of a? 50, because if I put a half in place of a, I'm saying when will the wound be 1/2 square millimeter? And that's not the question. When will it be 1/2 square millimeter? The question is, when will it be half of its original size? And if it started out as 100, when it's down to half its original size, it will be 50 square millimeters. So make sure you understand what A stands for. It's not a percent of original, it's a size. Based on the first thing that we had to do in 117, what do you think's the first thing we have to do in 120? You have to get the exponential expression by itself. Get the e to the negative 0.35 by itself. So divide by 100. 50 divided by 100 is 1/2, or it's easier to punch on the calculator, is 0.5. Then what? Same thing we did here. If you have exponential form and you're solving for n, you can change it to logarithmic form. In logarithmic form, I could use log base what? Log base e, which is abbreviated as ln. Natural log of what? Of 0.5, because it's always the exponent that's on the other side of the equation. Natural log of 0.5 equals negative 0.35 n. Again, all we did was change to exponential form. And since this was base e, when we changed it to exponential form, we had natural log. And then just divide both sides by the negative 0.35. N is the natural log of 0.5 divided by negative 0.35. And somebody tell me how long it'll take for that wound to be half of its original size. So darn close to 2 days. If this was a doctor talking to you in his or her office, the doctor would probably say, if this wound isn't about half as big in 2 days, you need to come back because your antibiotic's not working, there's an infection brewing, something. But this wound should be about half of its original size in about 2 days. Okay? Any questions? All right, there are 2 more problems I need to show you because one of them is definitely like a problem on the test. It's one of the most common applications of logarithmic scales. Number 128. In the paragraph right before 128, let me just show you. The decibel scale measures the loudness of sound. The decibel rating of a rock concert is a lot higher than the decibel rating of a funeral. Way higher. Most likely. The loudness of sound, L of X, is measured in decibels. let's see, the loudness measured in decibels of a sound of intensity X measured in watts per square meter is defined as the loudness is 10 times the log of X over I sub 0, where I sub 0 is 10 to the negative 12 watts per square meter, is the least intense sound that a human ear can detect. All right, I'm going to have to think about that one a minute. The loudness of sound. The decibel rating of a sound is found with this formula, 10 times the log of X over I sub 0. X is measured by, gosh darn it, I used to remember the name of the little tool that's used to measure the loudness of sound. It has a needle on it. It looks kind of like the seismograph of an earthquake, the needle that jumps up and down during an earthquake, only this is measuring the loudness of sound. So a little sound would have just a little zigzag across the screen, and a big sound would be jumping up and down. I think that's it, oscilloscope. Huh. That sounded so familiar. Okay, that measured sound. Oh, okay. All right. See, I can do the math, but I know a little about the physics of it. So that machine gives you a reading that measures the loudness of sound, and you put that reading in the place of X. You divide that by some I sub 0, which is given to you. That's called the threshold of human hearing. The smallest sound that a human can hear would measure on that little machine as 10 to the negative 3. So you put 10 to the negative 3 in place of I sub 0, the reading off the machine in place of X, and then you just punch this formula on the calculator to get the decibel rating of that sound. In 128, we're looking for the decibel rating of amplified rock music, which was measured to have an intensity of 10 to the negative 1 watts per square meter. Yes, sir. That was given to us, only that's not a 3, it's a 12. You know what? 10 to the negative 3 is coming up down here when we talk about the Richter scale rating, and I wasn't looking closely. It is 10 to the negative 12. All right, so 10 to the negative 12 is what you put in place of I sub 0. So number 128 gives us the intensity of the amplified rock music as being 10 to the negative 1. So the loudness associated with that rock music, which seems like such an old-fashioned term to even use. Does anybody say rock music anymore? It's something else. It's rap. I haven't even heard anybody say pop. Huh? It's that noise, yes. The loudness is 10 times the log of whatever reading I get off the little machine divided by the threshold of human hearing, which has an intensity of 10 to the negative 12. Now, this is function notation. This doesn't mean L times something. It means loudness of a sound of this intensity. I could pick up my calculator and punch that right now, but let's don't. Don't grab your calculator. Help me figure something out. You already know the quotient rule for dividing expressions with exponents. If you divide two expressions that have the same base, what can you just do with their exponents? Subtract. That's 10 to the negative 1 minus negative 12, or that's the same as negative 1 plus 12. What's negative 1 plus 12? Yeah, so that's 10 to the log of 10 to the 11th. And I could pick up the calculator now, but let's don't. What is log of 10 to the 11th? I'm not worried about that 10 for a second. I'm just figuring out the exponent of 10. That would give me 10 to the 11th. Yeah. Remember the log base 7 of 7 to the duck is just duck. Log base 7 of 7 to a power undo each other. So this log base 10 of 10 to the 11th, yes, you could punch it on the calculator, but you shouldn't have to. The calculator's just going to give you 11. And then the coefficient 10 multiplied by that 11 gives you 110 decibels would be the loudness of that music. Because the loudness was 10 negative 1, 10 raised. Uh-huh. We could just multiply the power base. Multiply the power and the base. I'm not sure what you're calling. What are you calling the power? But you had to get that 11 by subtracting -1 minus -12. Once you had that 11, yes, you can multiply that exponent times 10 because that's what log base 10 of 10 to the 11th means. Now, the decibel scale is called a logarithmic scale. It's a scale because it measures sound, and it's a logarithmic scale because its formula has a logarithm in it. The other common logarithmic scale is the Richter scale rating for earthquakes. Did anybody feel that earthquake last week in Kentucky? Remember, my husband and I were in town, and our daughters were at 2 different houses, and they both felt it, and we didn't. Kirk said it was because we were outside. We didn't have any of the things that were jiggling and making noise inside the house. I don't know. Both of my daughters felt it. Pretty cool. Instead of doing 132, because this problem just happened and some of you felt it, let me give you the formula for magnitude of an earthquake. Just like the logarithmic scale compares the intensity of any sound to the little bitty almost nothing sound, the Richter scale rating compares the intensity of an earthquake to what's going on in your driveway on a normal day. Now, even on a normal day, the rocks in your driveway are rumbling just a little bit. If a seismologist brought the seismograph and set it down in your driveway on a day that there was no seismic activity, it would still read 10 to the -3, or very little undetectable seismic activity. So that's just like the 10 to the -12 is the threshold of human hearing. Now, I used to not understand the difference between an earthquake rating of 4 and an earthquake rating of 5. Didn't seem like a big deal. 4 or 5, and it's about the same thing. But when I came to understand that the 4 and the 5 were exponents of 10, I can see that that's a much bigger thing. What's going on in your driveway in a normal day, the little bitty almost nothing earthquake compared to an earthquake of Richter scale rating 4, that would be 10 to the 4th, or 100,000, 10,000 times the rumbling that's going on in your driveway in a normal day. And an earthquake of Richter scale rating 5, your rocks in the driveway are rumbling 100,000 times what they would be rumbling on a normal day. When you look at it as the difference between 10,000 times the normal rumbling and 100,000 times the normal rumbling, that difference becomes much more apparent. So in Kentucky, No, I don't think I want to do it that way. We could find the intensity of the earthquake in Kentucky. Yes, I'm going to. A recent earthquake in Kentucky had a Richter scale rating of 4.2. How many times more intense was it than, or as compared to, the zero level earthquake? How much more rumbling was going on the driveways in Kentucky than would be on a normal day? Kevin, were you going to say something? Yeah, the 4.2 is the Richter scale rating. That's what goes here. This is a formula for a Richter scale rating. So put 4.2 in place of the magnitude of that earthquake. 4.2 equals log of, we're trying to find the intensity of the earthquake in Kentucky. So we need to compare it to the intensity of the little bitty almost nothing earthquake, and that was given to us as 10 to the negative 3. How can I solve that for x? You're right. 2. If this is logarithmic form, what are we changing it to? Exponential form, where the base is what? The base of log without a written base is understood to be 10. So in exponential form, this would be 10 to the 4.2 equals x over 10 to the negative 3. That's just changing it to exponential form. And then what one thing would we have to do to have that x by itself? Yeah, just clear out the fractions, multiply both sides by 10 to the negative 3. X equals 10 to the 4.2 times 10 to the negative 3. And I know because of my rules for exponents, when I multiply two expressions with the same base, I can just do what to their exponents? Add them, so 4.2 plus negative 3 is 1.2, and punch 10 to the 1.2 on the calculator. Okay, let's call it 15.85. The rocks in the driveway 100 kilometers from the epicenter. If we read this paragraph above number 128, it tells us that earthquakes are always measured, that the seismograph is always put down at a distance of 100 kilometers from the epicenter. 100 kilometers from the epicenter of this Kentucky earthquake, the rocks were rumbling about 16 times what they would be on a normal day. That doesn't seem really all that big now that I think about it. If we put in 10 to the 1.2 there, 4 point. No, that's right. Oh, oh, oh. I got what I messed up. It's not 16 times the rumbling that you're, yeah, what was I thinking? That's not 16 times the rumbling that's going on in your driveway in a normal day. That, on a normal day, the seismograph reading would be reading 0.001 millimeter, this big. The little needle's only going up and down this much. On this day, the needle's going up and down 16. Compare 0.001 to 16. That's way more than going on in your driveway in a normal day. This 4.2 is, let's see, 10 to the 4.2 would be over 10,000 times what's going on in your driveway in the normal day. That sounds more like it. 15,000 times the rumbling that's going on in your driveway in a normal day. That's more what I was expecting. All right, so I think you have a decibel problem and a Richter scale problem tacked on to this homework because I knew that we wouldn't get to them in the section 6.4 homework. The Richter scale problem you have to do is actually easier. I'm not going to write this one down because we need to move on. But the one that you're given, you just have to put the 7,943 millimeters in place of X and then just punch it on the calculator. Log of 7,943 divided by 10 to the negative 3. That will give you the decibel rating. You don't have to solve for X. All right, 6.5, properties of logarithms. For some reason, I felt like I should start this handout restating the definition of logarithmic notation, just to remind you of how to go back and forth between logarithmic form and exponential form. If I give you a logarithmic expression, y equals log base a of x, you can change it to exponential form. The base is a, y is the exponent, and a to the y gives you x. The properties of logarithms all follow from the properties of exponents. When you multiply two expressions that have the same base, what did you just tell me you do to their exponents? You add them. This property A says the log of a product can be written as the sum of two logs. That's because when you multiply two expressions with the same base, you add their exponents. That's exactly what this right-hand side is, adding two exponents. The second property comes from the quotient rule of exponents. If you divide two expressions with the same base, you told me a minute ago you subtract the exponents. Bless you. You subtract the exponents. So when you have the log of a quotient, you can take it apart by subtracting the two logs. Because a to the x divided by a to the y is a to the x minus y. This says subtract the exponents. This says subtract the exponents. And then the third property says when you have log of something to a power, you can bring the power out in front of the log and multiply it. That comes from the power rule of exponents. If you have a to the x to the r, when you have a power to a power, what do you do with the exponents? A to the x times r. This log base a of x, that is that. I almost said that wrong. Log base a of x is an exponent, and you're multiplying that exponent by r because of this power rule. These three properties are used to take logs apart and put them back together. And you might be thinking, why do I ever want to take them apart and put them back together? Well, if you don't go on to any other math, you'll probably never see why. But actually, it's very useful. When you're solving equations that have several logarithms in them, the equation's easier to solve if you put the logarithms back together as single logarithms. In calculus, when we're finding the derivative, whatever that means, the derivative of an expression, a logarithmic expression, sometimes it makes the calculus much easier if we take the logarithm apart. So if you're not going on to calculus, you'll never see the point of taking logarithms apart. You will see the point of putting them back together because that'll help us in 6.6 when we're solving equations. These other four properties we've really already talked about. Log base anything of itself is 1. All you have to do to see why that's true is change it to exponential form. Anything to the first equals itself. So what's log base 12 of 12? 1. Or log base 90 million of 90 million? 1. Log base buffalo of buffalo is 1. Log base anything of itself is 1. Property E says log base anything of 1 is 0, and it makes sense if you change it to exponential form. Anything to the 0, what do you already know anything to the 0 is? 1. Anything to the 0 is 1. So if I say, what is log base 7 of 1? What's the exponent of 7 that would give you 1? 0. What is log base 90 of 1? 0. Log base pickles of 1 is 0, because anything to the 0 is 1. And then this property F and G come from the undoing nature of exponentiating and taking logs. Anything to the log with the same base of x, this exponent and the log undo each other. A to the log base A undo each other and just leave you x. If I said 7 to the log base 7 of x, the 7 to the log base 7 would just undo each other and leave you the x. Or if I say log base anything of a to a, or excuse me, log base anything of that same base raised to a power, the log base anything of anything undo each other and leave you x. That will make more sense when we run into a problem where we use it. 2 important cautions to give you. I see this all the time. I see folks illegally distribute a logarithm. If you have log of x plus y, you can't just distribute log because this doesn't mean multiplication. This is not log times x plus y. Log is not a number, so you can't distribute it. It's just as illegal as saying x plus y squared. You know the most illegal thing you can do with x plus y squared, that's just squaring the x and squaring the y. If you really want to evaluate x plus y squared, you have to write it down twice and multiply it out. You can't just distribute an exponent through a sum, and that's why you can't distribute a log through a sum. A log is an exponent. The other thing you cannot do is take the log of a fraction by just taking the log of a numerator and the log of a denominator. If you want the log of a fraction, you have to enter it on the calculator as the log of a fraction and keep the fraction in parentheses, so you're taking the log of the whole thing. All right, I told you properties F and G would make more sense when you saw some examples. Here are some examples. Use the properties of logarithms to find the exact value of each expression. Don't use a calculator. You don't need a calculator. Number 14, log base 2 of 2 to the negative 13th. Now, if we hadn't just talked about these powers, I would say, what is the exponent of 2, which would give you 2 to the negative 13th? What's the answer? Negative 13. Log base 2 of 2, those undo each other and just leave you the negative 13. If you want to label it something, that's property G. That's what property G is saying. What about number 16? Natural log of e to the square root of 2? What would that be? Just square root of 2, because that's the same as log base e of e. They undo each other just like log base 2 of 2. That's property G as well. Number 18, e to the natural log of 8. What's e to the natural log of 8? The e and the natural log undo each other. That's property F. Property F says anything raised to the power of a log with the same base, the exponentiation and the logarithm undo each other and just leave you the x. All right, number 20, think about log base 6 of 9. Can you squint hard enough to tell me the exponent of 6, which would give you 9? There is one, but it's not a whole number. 6 to the first would give you 6. 6 squared would be way too big, 36. So I know it's 1 point something, 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 but that's as close as I can get without a calculator. I also can't evaluate log base 6 of 4 in my head. I can't tell you the exponent of 6 that gives you 4. So without the properties of logarithms, there's not much I could do with these. But with the properties of logarithms, is it property A, B, or C that tells me how I can put back together the sum of two logs? Property A deals with the sum of two logs. You put the sum of two logs back together as the log of a product. You multiply their exponents, the x times the y. So in number 20, I could put the sum of two logarithms back together by multiplying their arguments, 9 and 4. That would give me log base 6 of 36. And that is something I can evaluate without a calculator. What's the exponent of 6 that gives me 36? Log base 6 of 36 is 2. So even though we couldn't evaluate either of those terms individually, when we put it back together as a single logarithm, we could evaluate it. Number 22, is it property A, B, or C that tells me how to put back together the difference of two logs? Property B deals with the difference of two logs. You put the difference of two logs back together as the log of a quotient. You divide the arguments. So on number 22, that's log base 8 of, divide the arguments, 16 over 2. But 16 over 2 is just 8. And what is log base 8 of 8? Yeah. And you could put 1 as the exponent of this 8 to see why that's true. Log base 8 of 8 to the first, the log base 8 of 8 undo each other and just leave you that exponent of 1. All right, number 26. 5 to the log base 5 of 6 plus log base 5 of 7. You zoom. If I had 5 to a single logarithmic expression, if that was just 5 to the log base 5 of just one argument instead of sum of two logs, in other words, if I could put this exponent back together as a single log, then yes, I could say the 5 to the log base 5 undo each other. What would this be as a single logarithm? Yeah, that's the sum of two logs. Put the sum of two logs back together as the log of a product. Multiply the 6 times 7. That's 5 to the log base 5 of 42. What is 5 to the log base 5 of 42? 42, because now that I have 5 to the log base 5, a single logarithmic expression, the 5 to the log base 5 just undo each other. All right, the first problems in the homework are evaluating exponential and logarithmic expressions just by knowing that logs and exponentiation undo each other. And then you have some problems that practice taking logarithms apart. Write each expression as a sum or difference of logs. If I have the log of a product, two things multiplied together, I'm going to take it apart as the sum of two logs. If I have the log of a quotient, I'm going to take it apart as the difference of two logs. And this last sentence, express powers as factors, means if you have log of something to an exponent, bring the exponent out front and multiply it by the log. All right, number 44. That's the log of two things multiplied together. How do I take it apart? The natural log of x plus the natural log of e to the x. That's property A. The log of a product is taken apart into the sum of two logs. One of those terms can simplify further. What is natural log of e to the x? Because natural log and e undo each other. That's property G that says the log base anything of an exponential expression with the same base, just undo each other and leave the exponent. Make sure that you don't try to combine those x's and say that's the natural log of 2x, because you're only taking the natural log of that first x. You don't have to have it in parentheses, but if you need to make it very clear in your head, then put in the parentheses. Number 46, I can take the log of a quotient, two expressions that are divided, apart as the difference of two logs. Log base 2 of a minus log base 2 of b squared. That's property B. But because of this sentence, express powers as factors, when I see that I have log of something to an exponent, I'm just going to bring the exponent out in front of just that term. I can write that as log base 2 of a minus 2 log base 2 of b. That's using property C. I have a feeling that if you've never seen logarithms before, then right now I sound like Charlie Brown's teacher. I'm going wah, 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 and it's going. If you've never seen logarithms before, you're probably cursing in your head and just trying to get it all written down. What I would suggest that you do, now that you have it all written down, you could watch this video again at home and just listen. Listen without having to write. It's hard to write and listen at the same time, but you've already done the writing. So if you need to, watch the video again. All right, number 48. This is the log of a product. This is x times square root of 1 plus x squared. But something about the way those directions are written, express powers as factors, makes me think I want to write that square root as an exponent. What exponent means square root? Not negative, just 1/2. Anything to the 1/2 means square root. So I could rewrite that expression as natural log of x times 1 plus x squared to the 1/2. And all I did was get rid of the radical. Now when I take this expression apart, I can rewrite the log of a product. Do I take it apart as a sum or a difference? Yeah, look back up at the top of the paper if you need to. This is a product. Property A tells me to take the log of a product apart into the sum of two logs. So I could write that as natural log of x plus natural log of 1 plus x squared to the 1/2. And then what's the only other step I need to do? Because the directions say express powers as factors. Bring the 1/2 out front in front of that term. Just that term, not the whole expression, but just that term. that was my next question to you, actually. To bring this 2 out front, it would have to be the exponent of the whole argument. This argument is 1 plus x squared. The base of the 2 is only the x, not the whole argument. And you can't distribute natural log. You can't take that apart, natural log of 1 plus natural log of x squared. That would be this mistake. Since you can't do that, you can't bring the 2 out front because it's not the exponent of the whole argument. All right, one more of these, number 50. What exponent means cube root? 1/3. And I'm going to go ahead and do 2 things at once here. Not only change that cube root to the exponent 1/3, but I'm also going to go ahead and say when I have log of a quotient, do I take it apart as a sum or a difference? Difference. So that's log base 5 of x squared plus 1 to the 1/3 minus log base 5 of x squared minus 1. And it's important that I have that x squared minus 1 in parentheses, or else I'd only be taking the log base 5 of x squared, not the whole x squared minus 1. What's the only other thing I need to do to have satisfied those instructions? Bring the exponent out in front of that term. There's one other thing I'm going to remember to add, and one other example that I need to add to this handout, because folks miss this sometimes. You know to take the log of a quotient apart as the difference of 2 logs. That would be natural log of A minus natural log of BC. And folks don't usually have a problem with that at all. But here's the most common mistake. What's wrong with that? I thought you took the log of a product apart as the sum of 2 logs. Not quotations, but parentheses to show that that B and the C were both in the denominator. I either need to have that sum in parentheses to show that this A was divided by the B and the C, or I can distribute that negative and write the answer as natural log of A minus natural log of B minus natural log of C. Let me remind you of something that you learned about negative exponents. When we were talking about negative exponents for the very first time, if you saw A times B to the negative 1 times C to the negative 1, for example, then when we were first talking about it, you would have probably said that means A times 1 over B times 1 over C, because that's what the exponent negative 1 means. And then when I said, write your answer as a single fraction, you said, okay, that a's over 1. So if I multiply straight across, I get a over bc. But then after a little bit of practice, you learn to say any factor with a positive exponent is going to end up in the numerator, and any factor with a negative exponent is going to end up in the denominator, and you didn't have to write this step anymore. Remember that shortcut? The same thing is true with logarithms, only instead of saying anything with a negative exponent came from the denominator, you say anything with a negative coefficient came from the denominator. The fact that this natural log of b and natural log of c both had negative exponents, negative coefficients, that's what told me they both came from the denominator. That may help us when we're putting logarithms back together. All right, numbers 60 through 68, we're practicing putting logarithms back together. And the hard part is not putting them back together, it's cleaning up what you have after you've put them back together. For example, number 60, I know I could put those two logarithms back together as a single log. That means your answer should only have one log in it. I could put that back together by adding the arguments, subtracting the arguments, multiplying the arguments, or dividing the arguments. That's hard to say. Which one? Yeah, the sum of two logs is put back together by multiplying the exponents. And I don't mean exponents, I mean arguments. I'm sorry. That's using property A in reverse. And you can check it by using property A in forward. The log of a product is taken apart into the sum of two logs. And then just simplify this argument as much as you can. You multiply those two fractions together. You have log base 2 of 1 over x cubed. On the test, this would be absolutely fine with me. If I said write as a single logarithm, you've done that. That's a single logarithm. But just in case my math lab wants you to take another step, this didn't say express powers of factors, but something is making me think that my math lab may want you to do this. How could you write 1 over x cubed with a single exponent? What would the exponent of x be that would mean the same thing as 1 over x cubed? -3? And what could you do with that -3? Bring it out front. So for testing purposes, this is absolutely fine with me. But if my math lab counts it wrong, then I understand what it's wanting me to do. Write that with an exponent so that I can bring the exponent out front. All right. I am going to skip 64 just because it takes so long to simplify. Putting it back together is easy. It's just a single log, this fraction over that fraction. But how do you divide by a fraction? Multiply by the reciprocal. You have to go back to chapter R and remember how to divide by an algebraic fraction. You have to flip the second one, factor everything, cancel your common factors. So you should remember how to do that, or click example and view example if you need to, but it takes a while to simplify that. 68's the easiest. Let's go on to it. And then let me tell you about the change of base formula real quickly. And if we have time, I'll go back and do 66. 68's easy. We're doing the exact opposite of what we were doing in the previous problems. We're trying to put this back together as a single log. Where could I put these coefficients 1/3 and 1/2? So that I can put those two logs back together. Yeah, it looks just like this. If I have a coefficient of 1/3, it came from being the exponent of the argument on the line above it. So I would put this 1/3 back as the exponent of the x cubed plus 1. And that 1/2 back as the exponent of the x squared plus 1. Do I have a single logarithm yet? No, I still see two logs. I don't have a single logarithm till I put that back together as a product. This is the sum of two logs. Put the sum of two logs back together as the log of a product. I might need brackets here. X cubed plus 1 to the 1/3 times x squared plus 1 to the 1/2. I wonder if this is a typo because there's not really anything I can do to simplify this. If the bases were the same, if they were both x squared plus 1 or if they were both x cubed plus 1, what could I do to the exponents? Add them. But since they're not the same, there's nothing I can do to clean that up. All right, I'd like to get back to number 66. If I don't, then you'll just have to click the View Example button. It's putting back together and then cleaning up. But the one other thing I need to tell you about is the change of base theorem. What two base logarithms do you have buttons for on the calculator? Natural log is log base what? Natural log is log base E, and log without a written base is log base 10. So as of this moment, all you can enter on the calculator is log base E or log base 10. Well, we've evaluated things like log base 2 of 8 before, but we didn't need a calculator because 8 is a power of 2. We could figure out the exponent of 2 that gives us 8 is what? 3. So log base 2 of 8 is 3. But log base 5 of 18, I can't squint hard enough to tell you the exponent of 5 that'll give you 18. I can tell you it's bigger than 1 because 5 to the first is 5, but it's less than 2 because 5 squared is 25. It's something in between 1 and 2. That's all I can tell you. The change of base theorem gives us a way to change other bases to bases that we have on the calculator. Log base A of x can be changed to any other base. Log base something else of x divided by log something else of A. We usually just change other base logarithms to natural logarithms. In other words, I don't usually use that. I use this. Log base A of x is the natural log of x divided by the natural log of A. In other words, this log base 5 of 18 that I can't do in my head, I can punch it on the calculator as natural log of 18 divided by natural log of 5. And if you have trouble remembering which one goes on top, just remember the x is over the a here. The x is over the a here. The 18 is over the 5. And then punch this on your calculator. It should give you 1 point something, round to the nearest thousandth for me, 3 decimal places. 1.796. Does anybody second that? The great thing is it's checkable. Just raise 5 to the 1.796 and see if it gives you something darn close to 18. Yes, ma'am. I'm pretty sure this is right. Hang on. I'm sorry, what? Darn close to 18. It's not exactly 18 because we rounded this 1.796. Can you hang around 1 second after and let me see what you punched? It's just the darn backwards calculator. It'll be fine. All right, 74. I can't squint hard enough to tell you the exponent of 1/2 that gives you 15. I can tell you it would take a negative exponent to give you 15. Or I can punch it on the calculator as natural log of 15 divided by the natural log of 1/2. It'd be a little bit easier to punch on the calculator as natural log of 0.5. That'd be the same thing. Punch this one 15 and then your natural log button divided by 0.5 and then your natural log button equals. Somebody give me 3 decimal places. Negative what? All right. Darn close to negative 4. Does anybody second the 3.907? Okay. We could check it by raising 1/2 to the 3.907, and it better give us something darn close to 15. Oop, I left off my negative just in my check. Did you get it that time? Okay. I bet you could get the first one now. I bet you you punched something wrong the first time. Oh, okay. All right, we'll look at it then. And number 76, I can't squint hard enough to tell you the exponent of square root of 5. That would give you 8. But I can punch it as natural log of 8 divided by natural log of square root of 5. And on the fabulous backwards calculator, you're going to have to say 8 natural log divided by 5 and then square root and then natural log and then equals. Somebody give me 3 decimal places. Anybody second that? You should be able to check square root of 5 times 2.581 should give you something darn close to 8. All right. You should have everything you need to do the homework. We didn't have time to work one this ugly. Those of you who don't have another class and want to stay 5 more minutes, I'll do this one for you if you want to see one more. Those of you who have a class and need to go, just remember that we talked about these graphs in 6.4. Yeah, 6.4. Remember the graph of the logarithmic function has the critical point 1, 0. And if you have a graph that shifted to the right 3, that was nothing new. I don't know. What did you say?
Your conference is scheduled to end in 2 minutes.
I just misheard. I think y'all probably said the right thing and I couldn't hear you with this Bluetooth thing in my ear. All right. Try the homework. Watch the video again if you need to. Click View Example or click Ask Instructor. I will be